g of n. By the way, here is another interesting thing. This f of n equal to g of n plus h of n. What is the h of n for this guy n? Anybody who didn't realize this, make sure you realize this. If you are at the goal node, the cost of optimal goal node is 0. Unless you have major self-esteem problems. In which case you think, I'm a goal, but there's another goal which is better, so it might be better for me to go. No, not for you. You are already in your skill. And it's 0 cost for you to stay in your skills. Anywhere else you have to spend time going there. You see what I'm saying? So g of n for goal node will always, h of n for goal node is always 0. So f of n is really just g of n. And I'm basically arguing, I know that g of n is less than or equal to g of n double dash plus h of n double dash. We know this because that's what this thing said. Given this is true, can this be true? No. As long as h of n double dash, is less than or equal to h star of n double dash. H star of n double dash is supposed to actually compute exactly that distance. Do you see what I'm saying? As long as it is actually admissible, you are guaranteed to be optimal. This is the proof, that's it. It's just a little bit of arithmetic inequality. And essentially what it's saying is, by being optimistic about distances, you are guaranteed to be optimal when you find the first node that turns out to be a goal node. Optimism on cost gives you optimal solution. Pessimism on cost makes life easy. It's like I give you an exam. Say, oh, it's extremely hard, I'm not going to be able to do it. You're done, I get it. Because you're not going to be able to do, so why waste time? It's these other people who think maybe we will be able to do, and they'll struggle, don't see any movies over the weekend, and they actually work on the exam. Full-on pessimism essentially is computationally great. I mean, at the risk of not making fun, I mean, I don't want to make fun, but honestly, depression is a kind of full-on pessimism. And that ends computation in the worst case. Okay? So pessimism on cost basically might lead to inoptimal solutions. Optimism on cost is guaranteed to lead you to optimal solutions. That's it. Okay? And by the way, remember that this proof actually gave you proof both for uniform cost search, where I basically thought only in terms of G values, and A star, where I thought in terms of G as well as H values, as long as H is less than H star. You see? This is it. This is, as long as the heuristic is admissible, A star search is guaranteed to be optimal. And that's surprising. It's like, you probably didn't realize this before. Very surprising. Now the rest of it would be, where do you get these kinds of H values that are going to be admissible? The thing that I did for that little graph where I wrote numbers myself, that's a bad way to live life. Essentially, you have no life, you just go around and giving numbers to every search node. There should be an automatic way of computing the heuristics, given the model, and that's what we do. Okay, so this is, by the way, the actual proof, written down, so you can look at that instead of the other one if you want. Now, let me show you this to make sure that you get your intuitions about heuristics correct forever. Okay? Remember what I said. Heuristic is for all n. It's a function over nodes. Even though we think in terms of h of n, it's basically a function over nodes n. Do you see what I'm saying? So it's important to remember that you should see them as functions. So So here is an abstraction. On the x-axis are nodes. On the y-axis is the heuristic value for that node. I'll make up some functions. Okay? And I'll ask you some questions and you just very quickly answer. Okay. That is H star for this problem. First question, is there a goal node for this problem? Assuming these are the only search nodes, is there a goal for this problem? Why did you say that? There is no zero. Do you see what I'm saying? I made this a million years back, and at that time it was very hard to make these freestyle drawings. I didn't have this pencil. What I really should have done, obviously, is I should have made it like this. In which case it touches zero here, so it will be fine. But I didn't do that. Okay? So instead, I'm making lemons with lemonade. I'm saying lemonade with lemons, and I said I showed you an H star, and actually it corresponds to a problem which has no goal. But you know, be that as it may, let me ask you some other questions. Okay, let me ask you some other questions. So forget about this blue stuff for now. Okay, it's not there. Okay, here is a heuristic value. This is H1. Is that admissible? It's below the function everywhere, so it's admissible. H5. It's above the function everywhere. It's like pessimism all over the place. So you're always assuming that you have more work. Again, remember this. If you tell your boss, oh my God, every work that the boss gives you, you say, oh my God, it's too much work, you have very little work. Including not having a job, which is also not having work. You see what I'm saying? Because you'll be done. Oh, it's too much work. And you can say this to me too. It's too much homework, and you know, we'll see what I do. But, okay, so that's H5. Pessimism over cost is a great way of reducing computation. But it's not going to give you optimality. H4. It's admissible here, it's admissible here, it's not admissible here. In fact, that's a dumb thing to say. Admissibility is a for-all property. Do you see what I'm saying? It's not, you don't get to say, this guy was, you know, alive for some time, dead for some time, alive for some time. You're dead. You're dead, you're dead. Okay? Okay, so that's H4. That's inadmissible. Remember that. Okay, here is H2. Is that admissible? If I get to use either H2 or H1, which one would you use? That makes H2 more informed. Two admissible heuristics, H2 and H1, you would say H2 is more informed than H1 if H2 is always greater than or equal to H1. And you see why this makes sense, because if you're more informed, that means you're closer to H star, that means you'll take fewer expansions. More informed heuristics do less search. Okay? Right? That's fine. How about H3, this guy? So that is H3. In case you are not able to see, I'm going to put it in like this. That's H3. Oh, that's H2. Okay, and then I'm sorry. Let's see, this is the one that I used. And so this one. I'm doing the same thing now. That. Is that admissible or not? I'm sorry, actually the people who said no are correct also, because I just happened to cross here. So that's not there. In which case is it admissible? It is, right? For pedagogical purposes, you know, a teacher with shaky hands, you know, this is admissible. Now here's my question. If I have this blue guy and this green guy, I give you both these functions. Two heuristics you have. They are interesting trade-offs. In some places, the blue guy is bigger than the green guy. In other cases, the green guy is bigger than the blue guy. They're both admissible. Can you obviously think of a way of making a heuristic out of these two heuristics which is better than either of them? One obvious way is multiply the two heuristics. How many people want to multiply the heuristics? Better not. Okay. Or somebody wants to multiply. You're in big trouble. Because when you multiply, they could actually cross over H star in general. I mean, cross over the H star. Add the two heuristics. You would love to add the two heuristics. You really would love to. Most of the time, the heuristics that are given are not additive when they do it visibly. Then what else can I do? Max. You see what I'm saying? Max will basically look like that. It's basically taking the upper envelope of both the curves. If you have two admissible heuristics, H1 and H2, you take max of H1 and H2, that is no worse than H1 and H2 in terms of informedness. Simple idea. But do remember that you would have loved to add them. And so sometimes there may be problems where you can come up with heuristics from two different orthogonal kinds of abstraction that can be added. Then it will make life much, much happier. But normally you have to take max. Yes, sir. What's your name?
Kian.
Okay.
So, like by comparing H2 and H3, we can't say one's a better optimality than the other, but they are both optimal.
Yeah, there is no better optimality. Again, please don't say better optimality. They both get the same exact optimal solution. One gets done faster. Right? There is no such thing as better optimality. Okay? So one gets done faster. It does fewer node expansions, which we would love to have.
Can you tell by that function which one is faster though?
That's great. I mean, so in general, in a coarse way, informedness does guarantee fewer nodes expanded. But since you seem to be so interested, let me skip over these things and show you this question, please, and then come back. Here is a problem. H star, H1, H2. Which is more informed? Which is more informed? Informed is, no, H star, of course not. H star is optimal. Which is more informed between H1 and H2? H1, that's what we define. That is the whole point of trying to answer Kian's question. Right? So H1 is more informed. H2 is less informed. What does your intuition say if you were to do search? Which one do you think will actually do fewer node expansions? H1 or H2? How many people think H1 will do fewer node expansions? H1, which is more informed, but it assumes everybody is equal, does fewer node expansions. How many people think H2? There is a reasonable argument as to why H2 is better, right? Because it's almost mirroring H star. It's distinguishing between good guys and bad guys almost the same way H star does. Whereas this guy doesn't, everybody is equal. Okay? So in fact, interestingly enough, it turns out that informedness is too coarse a measure. If you are into this, basically there's a lot more you can do, which is in terms of you need to be able to realize that H1 actually is worse than H2. Because H2 almost is just like H star. I just wrote it that way. I basically took this, put it here, put it in red, in case that's not obvious. Right? So now here's the interesting question. Why would that happen? How could it be that a more informed heuristic actually do, quote unquote, more informed in terms of our definition, actually do more node expansions. That is actually answered here. The basic idea, and I'll say it here and maybe it will become clearer once we go through those other slides, is of all the nodes you expand, A star search, let's see if in fact it's, yeah. Okay. Stop. Okay. Remember, if you have a graph, uniform path search was going circularly. Right? A star search does, these are constant G values, constant distance values. That's why they're constant. A star search does constant F value contours. And the F value basically tells you if your goal is this side, nodes on this side are not good. Whereas G value contours will say everybody in the same distance is just as good. It's these contours that tell you everything on F value, lower F value, have to be expanded before anything on the higher F value. That's just the way A star works. You see what I'm saying? And in general, the reason, if you look at this picture, the reason A star is better than uniform path search is because it's more and more directed towards progress towards the goal. And in fact, for H equal to H star, these contours become essentially a line, parts of the line, parts of the path to the goal. Having said that, here is an interesting question. Remember I said every node on, so if the goal is at F star, that means the optimal goal has the F value equal to F star, which obviously will be just G star, because the goal will have H equal to 0. You know that A star search will expand every node whose F value is less than F star, for sure. That's how it gets to F star. It wouldn't have expanded even a single node whose F value equal to F star until it expands all nodes whose F value is less than F star. It's the same argument for uniform path search, except in G star instead of F star. Now, in terms of the nodes that the A star search expands, you can now separate the number of nodes it expanded into all the nodes whose F values were strictly less than F star, which were expanded. Those are called interior nodes. And the nodes which are F equal to F star. Just because a node has F equal to F star value doesn't mean it's a goal node. Remember, many non-goal nodes can come to the same F star by adding some Gn plus Hn where H is not actually 0. You see what I'm saying? And in the F star contour, there are no guarantees that an informed heuristic is guaranteed to look at fewer nodes than an informed heuristic, than less informed heuristic. All the interior nodes, for sure, it's guaranteed. But in some search problems, most of the work gets done in that last contour. There's just too many nodes which all have the same F equal to F star value. And there's only one or two of them are actually goals. And if you are not able to distinguish good guys from bad guys, which is what that previous slab kind of heuristic was, it will make quick stopover up until the interior nodes and then it gets stuck on that last. This is essentially a second order explanation of what happens in A star search. If you understand this, you really understand what's going on in A star search. If you don't understand this, you will still get a good grade in this class. Okay? Okay. So we did this, right? Next I want to spend the rest of the time, where do heuristics come from? Where do the heuristic bounds come from? And I already told you they come from abstractions. So some examples. Okay, for path planning on the plane, abstractions would be things like sort of simplifying the obstacle shape. For a puzzle problem, simplifying the movement. Okay? And different ways of simplification can give you better versus worse heuristics. So for example, let me just do this first. Okay. Here's a nice path planning problem and multiple abstractions for the same problem. Okay? So here is the I, which is the initial state. Here is the goal G. These are the arbitrary amoeba-shaped obstacles. Okay? And I'm trying to find the shortest path from I to G. You know that it's not straight line because the obstacles might be intersecting. You need to avoid them. This is done by every mobile robot, including Roomba. In fact, Roomba actually doesn't do any search. What it does is it hits you and then moves back. Right? So Roomba is a reactive thing. You know, Baxter, the robot going on its, on its wheels, Baxter is this huge, big Iron Man-like thing. If it sort of gently hits you, you're dead. So it needs to plan before acting. It needs to figure out what's the optimal path before, which doesn't kill people. Because normally that's a good idea. Before acting. And so they have to solve this problem in the plane. This stuff that I was trying to do, where I was trying to get to this guy who's looking at the guy in the black shirt who's looking at his laptop most of the time, I could do that essentially as a path planning problem. Now here's my question. I need to sort of do abstractions. One abstraction that I gave you is to remove all the obstacles. That's an abstraction. Actually, I forgot to show that there. Here's an abstraction, which is, this is I, this is G. Nobody there in between. That's the one that I was doing to get to that guy earlier. That will give you straight line distance. That's admissible. Okay? Straight line distance is just, you throw it into the formula. Right? I hope you still remember what straight line distance formula is. And you put the coordinates, x1 minus x2 square plus y1 minus y2 square, square root, that's the distance. And here is a slightly better version. What I did was I took all the obstacles and essentially approximated them to circles, circular obstacles. These are inscribed circles. If I find the optimal path between I and G in this, that would be costlier than I and G here. Do you see that? So this is a more concrete abstraction. It's like a, almost like, it's an oxymoron, like jumbo shrimp kind of a thing. More concrete abstraction. This is real abstraction, everything gone. Here I said, I'll leave you alone, but I'll put some circles inside. So there is some amount of obstacles I'm still taking into account. A little more concrete abstraction is always better in terms of informedness. But it increases the cost of computing the heuristics. Agreed? Okay? Then, here is another abstraction. Circles, basically, I wind up doing these circles, still humongous amounts of obstacles are left coming all over the place, and I'm being too optimistic. So here's the deal. If you're optimistic, when you are done, you will get optimal solution. But if you're too optimistic, you will never get done. This is like trying to do exam, saying, everything is easy, it's going to be zero cost, let me slowly work on each of the questions, and somewhere after the first question's first part, the 3 hours are over. If I give you, time of the universe, then you probably would have done well. But obviously, time matters in terms of how much time you take. So too optimistic, means you would never get done. If you get done, you will get optimal solution, but you will not get done in any given form. Okay? So this guy is a little too optimistic. This guy is the most optimistic. So heuristic cost is cheap. It's almost like h equal to 0. Okay, and the guy who is even more optimistic than this is to say, oh, IMG is always 0. I don't even have to take the straight line distance. Everybody is my friend. In which case, that's uniform cost solution. So then this. Here is polygonal abstraction for a polygonal approximation to the abstract. This is clearly little more concrete than this. It will also take longer time to do the path estimation here. But the path estimation here is actually going to be higher than the path estimation here, which will be higher than the path estimation here. This is your informedness. If you understand this, you understood both what informedness means and why it helps. Now here's my last question. Why don't I do circles like this? That looks like a kind of an abstraction. Do you understand what I just said? That was my question. Why are we only inscribing circles, not circumscribing circles? The real reason is in English, abstraction tends to mean just simplified. This looks like simplified. I put a nice big circle around you. But it's not the technical meaning of abstraction. Technical meaning of abstraction is there are fewer constraints deciding what is a feasible path. That means you have to remove constraints to come to abstraction. Do you understand what I'm saying? So in fact, in this particular room, I would have assumed one other way I could have abstracted everything out is that guy is there, I'm here, there's a black hole here. That's abstraction of some kind. Then I'll say, sorry, I cannot reach that guy because I can't go through the back. It's a huge, big obstacle between me and him. You see what I'm saying? So remember that we are using abstraction in the technical sense. Abstraction means removing constraints on feasible paths. And what happened when you circumscribed is you added at least a few constraints. Some paths that were feasible before are not feasible. That changes everything. Okay? Yes, sir.
There's no way to quantify
What?
the level of abstraction.
No, I'll tell you one more thing, essentially in a minute. Okay? But that will answer your question. Okay. So that's for the path planning problem. You understood this. Okay? And for the puzzle problem, the textbook talked about multiple heuristics. One is the number of misplaced tiles heuristic. Right? And the idea is, you remember let's see, do we have a puzzle problem? Yeah. So the puzzle problem idea essentially, don't look at this right now. The puzzle problem idea is, here is the blank, let's say, if this is the current configuration and this is what I want. I just count the number of tiles other than the blank that are in the wrong place. And that would give the minimum number of moves the blank has to make. Minimum. Do you see what I'm saying? Okay? Now, why is counting misplaced tiles an abstraction? Because you are acting as if tiles can walk through each other and get to their places. So you are making more paths than were feasible before. which is you're reducing the number of constraints. That's why number of display styles is an abstraction. But it counts, for example, 2, which is here, and it's supposed to be here. It counts for 1 display style. Whereas, let's say, what else can we look at? Let's say 9, which is here, and it only needs to be here, will also be just counted as 1 display style. But really, you might want to say that it's not just whether you're misplaced, but how far are you from your original place? Right? And so if I can walk through, if I can still walk through blanks, walk through tiles, then it's still the case that 2 requires more moves to get to its real place than 9, which only needs to go 2 places back. So the question, of course, is how do I measure this? How many spaces is 2 supposed to, how many moves is 2 supposed to make to get to its real place? This is where the famous Manhattan distance comes. Basically, it's just another way of saying that 2 normally could basically can go like this, go like this. I'm sorry, no, 2 can go like this and go like this. Right? To its real place. That means 1, 2, 3, 4, 5. 5 moves. You might say, well, that's not the only way it can go. It could have gone this way. That will also be fine. The only thing that I'm not allowing is 2 sort of shoot goes like this. That's not allowed. And the only place that's not allowed is, that's certainly not allowed, is Manhattan. For those of you who might remember, because well, Manhattan takes too big a mind share in every US person's mind, they basically have streets and avenues that are perpendicular to each other. And so it's a grid world. Manhattan is a grid, irregularly shaped grid. And in Manhattan, you essentially, to go from one place to other, you essentially have to travel over streets and avenues. Where does the analogy break down for those of you who remember Manhattan? How many of you have been to Manhattan? Okay. Yeah. So the guy from India is going to tell you all about Manhattan. So Manhattan has this thing called Broadway. Have you heard about Broadway? The thing about Broadway is it cuts through. It's one of the few roads that is actually not vertical or horizontal. It's the Broadway that makes this analogy go away. But otherwise, Manhattan really is a grid world. And the distance in grid world is not the Euclidean distance, but actually the Manhattan distance. Suppose instead of all this nonsense about Manhattan, I'll say I just used Euclidean distance.